Okay, good morning, everyone. So this is the tutorial for week 5, and this is about interpolation, okay? So as you can see that in question 1, we have to find the divided difference table. We have to find the Lagrange form, and then we have to find the Newton form of the interpolation polynomial. So we do it step by step, okay? So now let me share my piece of paper. Okay, so in the first question, now you have to define the Lagrange. So you have x is 0, 1, 2, and 3, and y minus 4, 3, 2, and 5, right? So you just define L1 to be x minus everything except the first point. So x minus 1, x minus 2, x minus 3. And then now you just have the first point here. 0 minus 1, 0 minus 2, 0 minus 3. Okay. And this one you can simplify it a little bit. So you got minus 1 over 6, and then x minus 1, x minus 2, x minus 3. Okay. Similarly, you can define L2 is x minus everything except the second point. So x minus 0, which is x, and x minus 2, x minus 3, and then you have 1 minus 1 minus 2, right? Well, actually, 1 minus 0 first, yeah, but 1 minus 0, just do 1, right? And then 1, sorry, the second point is we have, so you replace, so instead of x minus 0, right? Now you have 2 minus 0, yeah? Or should be, what do I say? I should say that the second point is 1 minus 1 minus 0, the first point, yeah? And then 1 minus 2, right? And then 1 minus 3, yeah? Sorry about that. So 1 minus 0 is 1, yeah? 1 minus 2 is minus 1, 1 minus 3 is minus 2. So then, so this one gives you just 1/2, right? And then you got x minus 2, x minus 3. Okay. And so on. So then L3x is, you got x minus everything except the third point. Yeah. So x minus 0, and x minus 1, and x minus 3. Yeah. And then now you put in the third point is 2, right? So 2 minus 0, yeah? And then 2 minus 1, then 2 minus 3, okay? And so you simplify it, so it's become minus 1/2, and x minus 1, x minus 3. Okay, and so on. So the last one will be L4. So the L4 is x minus everything except the last one. So x minus 0, x minus 1, x minus 2, and then you divide it by The last point 3 minus 0, yeah, and 3 minus 1 and 3 minus 2. Okay, and so therefore, I mean, you can simplify this to 1 over 6, and we want x minus 1, x minus 2. Okay, so that is how you define the Lagrangian basis for this problem. So how many points you have? 1, 2, 3, 4 points. Then you have L1, L2, L3, L4. Okay, and then the polynomial is just b equal minus 4 L1 plus 3 L2 plus 2 L3 plus 5 L4. So you can leave it like this, okay? Or if you have time, you can expand it. You can expand it and simplify it. So suppose you have the time to expand and simplify it, then you will get something like minus 4 plus 15x minus 10x squared plus 2x cubed. You can use maple T8. Sorry, you can use maple. You can use Wolfram alpha. You can do it by hand. It's up to you. But if you expand it, you can get a polynomial like this. Okay. And now for the Newton form, then we have to compute the divided difference table. So now everything is you need to stop in the. Well, I think you can stop in the expression, or you can leave it like this. It's up to you. I mean, it's not. I'm not very picky about this. As long as you write down the form exactly like this, okay, then you are okay, because then everything is well defined. Okay, so I'm not very picky that you have to plug it in this and you have to expand this. Just you can stop here. Then it's okay. Okay. And then now the Newton form. So now the Newton form, you have to do a bit more. You have to do by, well, you see, if you do it by hand, then I just give you some simple numbers so you can do it by hand. But, I mean, with the online exam, everything can be done using MATLAB. So what can I do? So you can, so put this into MATLAB and you can compute this divided difference table. Okay, but now I show you how to do it by hand, at least for this simple case. So this 4, so minus 4, 3, you can compute the divided difference by 3 minus 4 plus 4, 1, so give you 7. Okay? And then 3 and 2 here, you got 2 minus 3. Okay. And you divide it by minus 1, so you got minus 1. Yeah. And then you got 5 minus 2 divided by 1, so you got 3. Okay. Then for the next column, so you got minus 1 minus 7. Okay. So minus 1, 7. Divided by, you have to divide it by, you go this way, yeah. So 2 minus 0. So 2 minus 0, just minus 4. And for this one, you got 3 minus 1, so 3 plus 1. Okay, and so you have to take this 3 minus 1, so 3 minus 1 is 2. So you got 2. Okay, the last one is you take 2 minus 4 becomes 2 plus 4. divided by the very last one. Yeah, you go down this one, minus 0, so divided by 3. So 6 divided by 3 is 2. So everything is a whole number. So very simple calculation. And now you can put in, so now you identify the divided coefficient. Yeah, so this one is minus 4, 7, minus 4, and 2, right? Then you can write down the polynomial Q, okay, is, now remember the formula. So now let me just write down, but just assume that now you know the formula. Right? So X, so the first one is just Y1, second one is f of X1, X2, and then, X minus 0, okay? And then minus 4, X minus 0, and X minus 1. And then the last one will be plus 2, X minus 0, X minus 1, and X minus 2. Okay, so that is your Newton form. And then again, if you have time, you can see that you can expand this into minus 4 plus 15x minus 10x squared plus 2x cubed. So it's identical. It's identical to the expansion of the Lagrange form. So it shows you the interpolation polynomial is unique. Okay. And again, please check that you get the same polynomial. Otherwise, you don't get the correct solution. And another way to check is you can plug it in the value, x equals 0, then everything here equals 0, and then you get minus 4, x equals 1, and so on. Okay. So number 2 is identical question. You just change the number. So just for you to practice. So suppose you put x equals minus 2, minus 1, 0, 2, y equals 1, 4, 2, 4, and then you find the Lagrange form and the Newton form. So I just skip it. Okay. So this is a calculation question. And now we go to a question that requires a proof, a simple proof. So now suppose, so no question, yeah? So now suppose I have a function that I know the third derivative is bounded above by 3 on the interval 0, 2. Then I try to approximate f by, so interpolate, well, maybe interpolate, yeah, with P2. So P2 is the polynomial of degree 2, right? Over 3 points. So x1 equals 0, x2 equals 1, and x3 equals 2. So now I want to estimate the errors at 1.5. So remember, 1.5 is not the interpolation point, right? So you don't expect 0. So you expect that, this one, f at 1.5 and P2 at 1.5 are not identical. But I want to estimate the errors. So what theorem I should use here? So you remember what theorem we should use here? Anyone? Did you follow the lectures? So you just skip the lectures and you forget everything, right? So anyone? So you remember what theorem we have to use here? The errors, yes, the error formula. So if you the error interpolation, yeah. So now if you remember the formula is like this. So f of x minus Pn of x, okay, is f to the power, not to the power, so to the derivative of order n plus 1 at some point psi over n plus 1 factorial, right? Then x minus x1 multiplied with x minus x2 up to x minus xn plus 1. Okay, so this is the theorem. You know, we cover it in the end of interpolation. Yeah, but now what? Well, maybe we're just interested in absolute value, so we can take an absolute value of everything here. Now, what n should I use? So now what? Yeah, n equals 2, right? So if you put n equals 2, okay, and put x equals 1.5, yeah. Okay, then I have f at 1.5 minus p2 at 1.5. Yeah, absolute value will be, so n plus 1, yeah, so n equals 2. So this one just becomes the third derivative at some point xi. So xi is between x1 to xn plus 1. Okay? So over 3 factorials, and then you got absolute value, then x minus x1. So remember our x is just 1.5, right? Yeah. And what is our x1? So our x1 is just equal 0. So 1.5 minus 0. And then our x minus x2. So remember x2 just equal 1. 1.5 minus the last one is 2. Absolute value. Okay. So now everything here is very clear. You just plug it in. How about the third derivative here? So how do I handle the third derivative? That's xi. So xi is between x0, x1 and x3. So how do I handle this term? So how do I know that f triple, yeah, less than or equal 3? Yeah, now you have to use assumption. So because we want the estimate only, right? So let's say that the third derivative absolute value less than or equal 3. So just say that, okay, less than or equal 3, and 3 factorial just equals 6. And now everything is now just a positive number here. So 1.5, 0.5, and 0.5. Okay. And then this one gives you a number. So this one, the number will be 0.1875. Okay. Yeah. So that is just the application of this error formula for the interpolation. Yeah. And now we move to the next question. So the next question will be question number 4. So question number 4 say that the map that you see, suppose you have a function f, a continuous function f, right? And you map it into the Lagrange interpolation, right? So the Lagrange interpolation is defined to be the sum of f of xi, li, I from 1 to n plus 1. Okay. And then this one we define a map L. So then what is the domain? What is the domain of the map? So the domain of the map is the set of continuous function, right? From say from A to B. Yeah. And it just mapped to the set of polynomial. Okay, so maybe we say polynomial of degree n from A to B. So remember in first year linear algebra, right? First year algebra, you have a linear map that map from a vector space Rn to our Rm. Remember? Yeah. So, you know, so recording first year algebra. You have a map T, that map from Rn to Rm, right? Yeah. Then, you know, like you take a vector x and then you map it to another vector by a multiplied by x. X is a matrix, something like this. Yeah. So a is the matrix. A just a m by n matrix. Yeah. Okay. So how you remember in first year, how do you show that the map is linear? So the map is linear when you show that T of alpha x plus beta y is alpha t x plus beta ty, right? And you say that is a linear map. So you remember? So this is from first year algebra. Yeah. So now the concept is the same. Yeah, the concept is the same, except that before you have a finite dimensional space. Here we have an infinite dimensional space. You know, the set of continuous functions is a set of infinite many continuous function over the interval, right? And then you map it into the finite dimensional space of polynomials of degree n. Okay, so we can think the interpolation is, I mean, the Lagrange form of the interpolation is a linear map like this. And now we have to prove it. Okay, so that is the idea of this question. So then how do we prove it? So now, again, we have to show that. So we want to prove that L of A F plus BG. Okay, so A and B are real number. Yeah, and F and G are just continuous functions. So continuous function on maybe say some interval 0, 1 or something like this. So it's not important here because I don't want to use A and B again, right? Because A and B we use it as a real constant here. And then we have to show that L of the linear combination of F and G, you know, it's just A L F plus B L G. So that is what we want to prove. Yeah. So how do we prove it? So we prove it by no. I mean, just for example, because I don't want to use A and B, just some interval, you know. So maybe it's better to say that it's continuous over C of x1 up to xn plus 1, right? Because we have, just for example, I mean, it's not very precise here, yeah, but assume that it's continuous over some intervals. You know, you can take x1 to xn plus 1, yeah. So then this is the linearity we want to prove. So now we go back to the left hand side, right? And now by definition, then L of this polynomial is just, sorry, L of this function, yeah? It's just this function you apply at the point xi, right? Multiply with Li. So Li is the Lagrange basis function, yeah? So, okay. So this one just by definition, from the definition, yeah? So definition, okay. And then now you can split it into two sums. AF of xi, Li, I from 1 to n plus 1, plus sum of be g of xi li, right? And this one is possible because the sum is linear. Okay, the sum is linear. So you can split like this. The sum is linear, right? And then now, so remember, I just a real number, and it's multiplied for every term. So you can take a outside. So this one is just a property of real number. Yeah. And similarly, you can take b outside as well. From 1 to n plus 1. Yeah. Okay. But then what is this one? What is the first term here? So what is the first term here? Yeah, just ALF, right? By definition. So this one ALF. And the second one is just BLG. That's it. So you have proven. So just prove it by using the definition and the linearity of the sum. Okay. So show that interpolation is a linear map. Okay, so interpolation process is a linear map. And you see, I mean, this one is just a generalization of the concept of linear map. You've seen it in first year algebra. Okay. Except that in first year algebra, you have a finite dimensional vector space to another finite dimensional vector space. But here, the domain of the map L could be the infinite dimensional space of continuous function. Okay, so that is the key point here. Okay, so now number 5. So number 5 is interesting. So now, suppose I have the Lagrangian. Yeah, so suppose I have x1, x2 up to xn plus 1. And I have the Lagrangian Lix. And now the claim is sum of Lix I from 1 to n plus 1 is identically 1 for all x. Okay. So now we have to see whether this is true or not. So now suppose I have only 2 points, x1 and x2, right? Okay, so make the simple case n equal 1. N equal 1, you just have x1 and x2, right? Okay. Then what is my L1? What is my L1 in this case? And what is L2 in this case? What is L1? What is L1 in this case? Anyone? No, L1 is not x1. So L1 is x minus everything except the first point, right? So it should be x minus x2 over x1 minus x2. Yes, correct. Yes. And then what is L2? So L2 is x minus everything except the first point. Yeah, sorry, except the second point. Yeah. So x minus x1 over x2 minus x1, right? And so now if I take L1 plus L2, then I just have x1 minus x2, the common term here, then x minus x2, then the flip the sign, so minus x plus x1. Okay, and you see that x here minus x cancel. And your x1 minus x2, x1 minus x2 is equal 1 for all x. Right? So the x got cancelled, just equal 1. So it's true for n equal 1, right? So if you have time, you can try to prove it for n equal 2, or you can check it for n equal 2, n equal 3, and so on. Yeah, but now we want to prove it in a general case. So how do we show it in a general case? So how do we prove it in a general case? So the hint is you have to choose some special function f. So what special function f? Let yi, yes, if you let on the yi to be 1, yes, agree, yes. So now if you choose on the data point to be 1, yeah. So now if you choose f to be equal 1 for on x, yeah, then the interpolation, right? The interpolation polynomial, Pn is given like this. So Pn is, remember, a sum of f of xi li, right? I from 1 to n plus 1. And now you have all of them equal 1. So it's just a sum of li, I from 1 to n plus 1, yeah? Okay, so now what's so special about this Pn? So maybe this one should be Pn of x, yeah? Well, it's equal 1. That's what we want to prove, right? So the interpolation property just give you that Pn of xi, okay, equal f of xi equal 1. So it means that Pn equal 1 only on n plus 1 points. So how do you know that it's equal 1 everywhere? For I from 1 to 3 up to n plus 1, yeah? So then how do you show that it equal 1 everywhere? You see, because you can have n plus 1 point like this, yeah? And the function equal 1 at every point like this, but it could go up and down like this, right? So you know, like x1, x2, x3, x4, and all of them equal 1 here. Yeah. So how do you show that Pn actually is 1 everywhere? You see the delicate point here. So you choose f equal 1 is a good start, yeah. But it's not enough to say that it's over. I mean, then the sum of Li equal 1 everywhere. You just got the sum of Li equal 1 on xi. Yeah. So how do we show that? How do we show that it equal 1 everywhere? So what is the key point here? Okay, so maybe we go back to the case n equal 1, right? Just go back to the simple case n equal 1. So you have L1, right? And L2, right? So you sum it up, then it equal 1. Yeah, so you have a cancellation here. But now, I mean, for general L, I mean, it's not easy to expand it out, right? You can, but it's very messy. But now you look at the L1. So what degree of L1? Is L1, what degree of the polynomial L1? Degree 1, yeah? What is the degree of L2? So then what is the degree of L1 plus L2? Degree 1. So degree 1, and it equal 1, you know, at 2 points, yeah? So degree 1 is just a line, yeah? Okay. So now you know that, you know, I mean, when a line that connect 2 points and they are 1, yeah? Then the function has to be 1, right? Well, unless the parabola, there is another story, right? But now, because the degree is 1, so it has to be the straight line. And the straight line, when you connect 2.11, then it has to be identically 1. So that's something to do with the degree of a polynomial, right? Yeah. And so now you go back to this. Go back to this, yeah? Then what is the degree of sum of Li? No. Why is 1? Before this is a special case, yeah? Before you have a special case, L1 and L2 are given like this, yeah? N, yes, because remember the Li, if you write down explicitly, Li is the sum, not the sum, the product of x minus x1, you know, x minus xn plus 1, except the xi, right? And then you have xi minus x1. So you have a degree n, yeah? And so the sum of Li, so the degree of Vn is the sum of Li, yeah? It just equal n, so degree n, yeah? And so now I have n plus 1 point, yeah? Okay? And then all of them equal 1. So can I have this situation or not? So can I have a situation like this? Or it has to be a straight line. So yeah, it must be straight, but that is what we want to prove, right? So we have to be a bit rigorous. It has to be straight, yes, but that is what we want to prove. So how do we prove it? You know, you said must be true, okay, but it's not a proof. Okay, it's like proving, like, you know, it has to be true, then therefore it's true. It's not a proof, you know. So how do we prove that? It has to be identically 1. And you can see, you know, so suppose you take n equal 2, right? Yeah. Then you have 3 points, yeah. You got x1, x2, x3, right? And you have, so degree 2, right? So degree 2 is a parabola, right? No, it cannot be degree 1. No, I don't say that degree 1. I said equal 1, but it's not. It has to be degree 1. Actually, you know, because of this, actually the correct statement should be said that the degree less than or equal 1, right? Sorry, less than or equal n, because you might have cancellation, right? But from this formula, okay, the degree has to be equal, you know, n, the sum of Li, right? So the degree of Li is exactly n, right? But when you sum it up, then the degree could be less than or equal n, because when you sum it up, some cancellation can happen. Okay. So, so now that is what we want to prove, right? We want to prove that suppose 3 points, then you cannot have this behavior. If there's n plus 1 point, that must be straight because there can be maximum n turning points even degree n. It's more or less it is the correct spirit, but we have to be more precise. Okay, I mean, maybe let me prove it. Okay, because now we don't have a lot of time, but let me prove it like rigorously. Okay, so now suppose I take q. Okay, but you see the point here. The point here is you have to prove it, right? Because from the interpolation property, you just have it equal 1 at the interpolation point. Yeah. But now you want to prove that it will one everywhere, then you have to do a bit more, right? So now let me define Q to be Pn minus F, right? So maybe Pn of X minus F of X, yeah? Okay, so then I have, well, actually F is just 1, right? So just Pn X minus 1, yeah? Q of X, okay? Then what is the degree of Q? Well, degree of Q is just degree of Pn. So degree of Q is less than or equal n. Yeah. So then you also have Q at xi, which is equal Pn at xi minus 1, which is equal 0, right? And I from 1, 2, 3 up to n plus 1. Yeah. So then by the fundamental theorem of algebra, okay, so now we have to say that by the fundamental theorem of algebra, yeah, then you can factor out Q like this. So x minus x1, x minus x2, and so on. But where do you stop? So where do you stop here? So fundamental theorem of algebra, yeah, stop at xn, right? Say that a degree n, right? Then you can have a linear and linear factors like this, yeah? So then now you say that q of x1 equal q of x2 equal q of xn equals 0, definitely, right? You just plug it in. But we also, the last point, q of xn plus 1 also equals 0 as well, yeah? But q of xn plus 1 equal a xn plus 1 minus x1 up to xn minus 1 minus xn. You see, so now the delicate point is the last point, yeah? So now we have to assume that all the points are different. Then the constant a has to be equal 0. So the constant a has to be equal 0. So therefore, q is identically 0 for on x. You see, so the degree n is very important. Well, actually, degree less than or equal n is very important. Otherwise, you cannot use the fundamental theorem of algebra. Yeah. And when q equals 0, that means that Pn has to be identically 1. Yeah. So without the precise degree n and the point xn plus 1 also interpolation point, then you cannot have this property. Okay. And so therefore, therefore sum of, so the conclusion is sum of, so P n is sum of Lix has to be equal 1 for all x. Yeah. So that's the proof. Yeah. So any question about this one? No more? Okay, so question 6. So question 6 is just application of question 5. So suppose I have f interpolate at xn xn x1 up to xn plus 1, then f minus bn just equals sum of fx minus f of xi li. You have to prove this. Okay. And then the hint is just use question 5. So how do you do this? You see that Pn is this one already, yeah. So the second sum just give you Pn. Okay. So how about the first one? So the proof you can use the right hand side and you go back to the left, yeah. So sum of fx minus f of xi li I from 1 to n plus 1. Okay. We split it into two sums. Minus f of xi li 1 n plus 1. Yeah. Okay, so you split it into two sums. Yeah. So what is the next step? Yeah, take fx out. Yeah. So because fx now doesn't depend on I, so you got f of x, sum of li, I from 1 to n plus 1, minus sum of fx I li. Right? And by definition, this one is just Pn, right? And this one we prove it equal 1. Yeah. So then you just have f of x. And that's it. So we this is a simple application of the previous question. Okay. And we don't see the use of this equation now, but you will see it in the next topic. We use it to derive for quadrature for Newton quadrature. So when we use results in question 5 in exams and other tutorial. Well, actually, in one of the past exam, I just gave that, as an exam question for you to prove it again. So, I mean, the proof is not complicated, right? Yeah. Okay. So that is on the question now. So unless you have any other question, we can stop here and you can ask me other question. So maybe let me stop the recording and I can let you ask any question you might have, right? So let me stop the recording. Okay, so let me stop.